Here is section 1.3 of chapter 1 for our week 1 notes. So, we're going to talk about uncertainty in measurement, which basically means we're going to talk about significant figures, or what we like to call sig figs. Okay. Counting is the only type of measurement that is free from uncertainty. The results of a counting measurement is an example of an exact number. The numbers for defined quantities, which we use in conversion factors, are also exact. For example, we know that 1 foot is exactly 12 inches, 1 gram is exactly 0.001 kilogram, and 1 inch is exactly 2.54 centimeters. So these are considered exact numbers. Numbers measured by any other method than counting are inexact, and these are the numbers that we're worried about with significant figures. The uncertainty associated with the measured number is generally plus or minus 1 in the place of the last digit. So it's like an estimated digit at the end. It's one that we don't know for absolute sure. It has to be an estimated number. To measure the volume of liquid in this graduated cylinder, you must mentally subdivide the distance between the 21 and 22 marks into tenths of a millimeter, sorry, milliliter, not millimeter, and then make a reading estimate at the bottom of the meniscus. So you can see here, this is our meniscus. The meniscus is the bottom of the curve that is formed by a liquid. So you know that this is between, and you can see on this part here or on this part here, that it is above the 20 and the 21. So here's our 21 right here. You know that it is above 21, but it is below 23. So it is somewhere in between there. So we are certain that it's above 21 and below 22, but what we are uncertain of is where exactly it is there. And that is our estimated number. So for instance, sorry, let me go back to this. For instance, this is most likely what we would consider to be 20 point, it could be 6, so 20.6 maybe. But we know that this number could be plus or minus the point 1. So it could be technically 20.7 or it could be 20.5. This last number is the estimate. So with significant figures, each of the digits is a measured number, including the uncertain digit, and each of those are a significant figure. So the ones that we are absolutely sure about and the one that we estimate at the end, these are all significant figures. Now, there's certain rules for significant figures, and a lot of students find these to be a little bit just hard to remember all the rules. But I promise that the more you practice this and the more you think about it, the easier it gets. So there are certain numbers that are always significant. If the number is not a zero, meaning 1, 2, 3, 4, 5, 6, 7, 8, 9, then it is significant always. Captive zeros, which we say are zeros between two non-zero numbers, such as this one right here, those are always significant. Those are always significant. So always, always. Now, when there are trailing zeros, trailing meaning at the end, they are significant if they are to the right of the decimal place. So see here, We have a decimal place, and we have a trailing zero here that is to the right of the decimal place. So it is significant. Also, when they are in scientific notation. Now, if you don't remember what scientific notation is, we can take this number right here, and if we put it into scientific notation, we find the first number that is after that zero when we're talking about a small number. So we would say 8.020, and then we count over how many places we moved that decimal. So we moved it one, two, three places over. So we would say times 10 to the -3. Because we're dealing with a very small number, that's why this is negative. A small number less than zero, you get a negative exponent. Okay. So these zeros, this trailing zero is in scientific notation, so it is also significant. Okay. So this one is significant because it's to the right of the decimal. This one is significant. Again, it is to the right of the decimal, but it's also trailing in a scientific notation. Now we can look at this zero right here. It's trailing, but it is not to the right of a decimal. It is to the left of the decimal. So as you'll see on the next slide, this would be considered non-significant. Non-significant. All right. So these numbers are always not significant. Leading zeros, meaning zeros before the first non-zero number. So leading zeros are zeros before the first non-zero number. Okay, those are always not significant. Okay, and this is something you can look at and use scientific notation to help you. Remember on the last slide, we took this number and changed it to scientific notation. And we did that by moving the decimal behind the first non-zero digit. So we ended up with 8.020. So the fact that we could leave out all of these zeros tells us that they are not significant. And so that's another way to kind of look at your zeros and determine if they are significant or not. Another not significant number are our trailing zeros if they are on the left of the decimal place. So like I told you in the last slide, this one, we have a assumed decimal right here at the end. This zero is to the left of the decimal, so it is not significant to the left of the assumed decimal. It is not significant. Okay. Now, this means when they are assumed uh, decimals, then it is not significant there. And basically, what that means is that this number is kind of you can think of it as a rounded number. This could actually be 3090.45, but we have, based on our measuring device, no way to know that it is that, or no way to know that this was, if this was actually um 3092, but it wasn't specific enough, our measuring device, to know that, so we couldn't put the two. We had to round this, and it's closer to not that, to 3090 than it is to 3100. So this is the number we had to go with based on what we were seeing. Starting with the first non-zero digit on the left, count this digit and all remaining digits to the right. This is the number of significant figures in the measurement unless the last digit is a trailing zero lying to the left of the decimal point. So let's look at this. And I promise the more you do um, practice on this, the better you will get at it. And I will continue to help you throughout, especially in our first few labs, talking about how many significant figures we have in a measurement or an estimation. So let's look at this one first. Okay, we'll look at this one first. So notice there are no zeros in this. They are all non-zero numbers. So that means all of these numbers are significant. So we have four sig figs here. Now let's look at this one. It's number two. Okay, here we have two zeros to the left of the decimal, and then we have, I mean, two non-zeros, I'm sorry, two non-zeros to the left of the decimal, and then we have one right of the decimal, 1 0 to the right of the decimal. That means that this zero is significant, so this is three significant figures. And basically, the way I think of it is when you have a number like this where they take it and they put 55.0, that means that your measurement was directly, if you think back to the graduated cylinder, was directly on the 55 point. So that's why we estimated to point 0. It wasn't up here, it wasn't down here, it was directly on the line. Now let's look down here at the bottom left corner, number 3. So we have the number 70.607. Now, the fact that we have these three numbers behind the decimal point, and within those three numbers, there is a zero. Remember, we call that a captive zero, or I like to call it a zero sandwich. That means that those three are all significant. Here we have two numbers to the left of the decimal point. Oops, I accidentally swiped back. Sorry about that. We have two numbers to the left of the decimal point, but even though we have a decimal point there, this zero right here, this zero is still in a zero sandwich because it is between this 7 and this 6, which are non-zero numbers. So that means that all of these numbers are significant. So this is 5 sig figs. Here we have number 4. We see that we have three numbers before the first non-zero digit, and that means that these three numbers are not sig figs. They're not significant. So anything starting after the 8, because it is after a decimal, anything starting after that is going to be significant. So here we have 6 sig figs. And this zero right here matches a whole nother rule as well, which is captive zeros or zero sandwiches. It's in between two non-zeros, so we knew it was significant. So, captive zeros result from measurement and are therefore always significant. Leading zeros are never significant because they merely tell us where the decimal place is located. Okay, let's do a few problems right here, just a few practice problems. If you want to pause the video for just a second and go through and try to figure out the number of significant figures for these, you can. I've also given you a helpful handy tip here for how to do scientific notation, which might be a good thing for you to make sure that you've practiced and know how to do. Okay, hopefully you paused the video and worked on some of these. So let's look at this first one. This first one is going to have three significant figures, and that is because these first three are not significant. The 4 and the 5 are non-zero numbers, so they are significant. And this 0 is behind a decimal point and behind non-zero numbers, so it is significant. For number 2, we have 5 significant figures, and that is because we have 2 non-zeros. We have a 0 sandwich, which is to the right of the decimal. And then we have this one, which is where I think is probably the most tricky for people. But because this is to the right of a decimal place and behind a non-zero digit, it is also significant. Now here we have 100.0. So here, this one is one that often students get mixed up on. This is 4 significant figures, and that is because all of these zeros are following a non-zero number, and we took the time to put a decimal and a 0 behind it, which means this is not a something that has been rounded. This is something that we know is going to be for certain, or it's our last uncertain digit, but it is what we know. We could not go any further than this. So these are, remember, 3 certain numbers and 1 uncertain number gives us 4 sig figs. Here, if you said 4 sig figs, you were correct. These first 2 zeros are just to tell us where the decimal is. The significant numbers start here with this 6. This is significant because it is in a 0 sandwich. And this is significant because it is after the decimal point, to the right of a decimal point. Now, this one is important because it does not have a decimal point at the end. So this one means that all of these zeros, because there is no decimal, are not significant. Not significant. Okay. This 5, of course, is. This 2, of course, is. And this 0 is because it is captive. It is held between 2 non-zeros. Now, so that means that this has 3 significant figures. You could also take this number and turn it into scientific notation, which, if you remember your rules of scientific notation from math or high school or whenever, or you use this chart over here, you know that this number would be 5.02 times 10 to the fifth. It's a positive because it's a large number, positive exponent, because it's a large number. And the exponent is 5 because our assumed decimal is here, and we would have moved it 1, 2, 3, 4, 5. Oh, I got that wrong. Strike that. This is 5.02 times 10 to the 7. I'm sorry about that. It should go here behind the 5. So then we have 1, 2, 3, 4, 5, 6. I missed it again. It's 6. You can tell that I've been cooped up in the house all day and I'm tired. So let's just mark that out and write it again. It is 5.02 times 10 to the 6. Okay. And the whole reason I brought that up is because if you look at this, then you can see that there are 3 sig figs, even though I was having trouble with the exponent. So we moved the decimal 6 places, and that was 5.02 times 10 to the sixth. All right. There are specific significant figure rules for mathematical problems. Really, the one that we use the most is this one in multiplication and division because that's what we're most often doing in chemistry. But if it's in addition and subtraction, the answer cannot have more digits to the right of the decimal point than any of the original numbers. So if you look here, this number has two digits to the right of the decimal point, and this number has three digits to the right of the decimal point. So when we add them up, like we learned how to do in elementary school, we end up with the number 102.731. But we know that we cannot have more than, so cannot have more than two past the decimal. So that means we have to round this. We have to round this to 102.73. Now, I know this probably seems arbitrary to you right now, but the reason we do this and the reason you didn't do this in math class is because when we're dealing with numbers in science and in chemistry, we're dealing with measurements that came from a measuring device. And so, yes, if you were in a math class, this number would be the correct answer. But when you're in a science class, remember the calculated answer cannot be more precise than the least precise measuring device. So your number cannot be more precise than your least precise measuring device. So obviously, in this problem, this was our least precise measuring device because it only went out two places past the decimal. So that meant that our final answer could not go more than two places past the decimal. Here on the next one, you see that we have 143.29, and then we have minus 20.1. So the second number only has one number after the decimal point. So even though when we do the math, we get 123.19, our final answer would have to be rounded to 123.2. Okay, I find just in my mind for some reason that multiplication and division is a little bit simpler because the number of sig figs in the final answer is determined by the original number that has the smallest number of sig figs. So for this, you just have to be able to count sig figs and know that you're going to have to round your final number to that. So you can see in this example right here, we have two sig figs here and we have four sig figs here. So that means our final answer cannot have more than two significant figures. So we see here, if we just put that in our calculator, we get 11.2154. Well, we know, oh, sorry, we know that it cannot be more specific than our 1.4 here, which had two sig figs. So that means we would round this number to 11. 11 would be our final number. Here we see we have four sig figs divided by five sig figs. And when we type that in the calculator, it'll punch out this really long number right here. But we know that our final answer cannot be more than four sig figs. So I go here and I look at the fourth significant figure, and I notice here that the number after that is a 5. So that means I'm going to round this number to a 3. So that gives me 0.03783, which would be four sig figs. A few additional things to remember are exact numbers can be considered to have an infinite number of sig figs, so they don't limit us. So, for instance, if we're working a problem like this where we say three pennies each have a mass of 2.5, well, 2 sig figs is what our answer would be in because this number 3 is an exact number. You don't have 3.1 pennies. You don't have 2.9 pennies. We know that a penny is an exact thing. It's accounting, so we have an exact number. So for this one, you would be able to use 2 sig figs because that's what it was used. In calculations with multiple steps, you round the result in each step can lead to rounding error if you do that. So you should always wait until the very end to do the actual rounding, or you may end up with an answer that is a little bit off of where you want it to be. Now, on your online textbook, if you look on page 18, there's a really good example of this. I didn't write that into the notes because it's just pretty long or a little bit longer, but the textbook breaks that down really good. So if you will look at the Alex textbook, then you can see that. All right, and then only numbers in the problem affect the number of significant figures. So let's look at this problem down here. If we're doing a conversion from 545 meters to kilometers, we would use a conversion factor, which is what we're going to talk about in our next little section. We know that there are 1,000 meters in 1 kilometer. Well, if you look at this, 1 kilometer is only one sig fig, and 1,000, because it doesn't have a decimal, would only be one sig fig. But this is a conversion factor. So this does not affect our number of sig figs. Only numbers that are in the actual problem can affect that. So we know that our final answer can be 3 significant figures. So in this case, we know that it would be 0.545 kilometers, and that would be 3 sig figs. Here's some practice problems for you to do. So if you want to take a minute and pause the video and work on those practice problems, then now would be a good time. And there are also a lot of worked examples in the book. All right. Hopefully you finished these. If you type this into your calculator, you would have got 39.68, but you see that we have 3 sig figs here, we have 2 sig figs here, so that means this number has to only be 2 significant figures. So instead of 39.68, I would have to round this to 40. Here in number 2, we see we have 45.6 divided by 1.23. If you type that in your calculator, you should get 37.073. So we see that that number has 5 sig figs, but this has 3 sig figs. This has 3 sig figs, so that means our answer can't have more than 3 sig figs. So we would have to round this to 37.1. Here we have 6.50 plus 2.4. Now remember, in addition, we are just focusing on how many numbers are after the decimal. So if you, sorry, my hand keeps flipping that. So if you were to do this, you would get 8.9, which actually has the correct number of sig figs because it only has one number to the right of the decimal, and we know that that's all we can have. So that number is good. If we do 18.27 minus 3.6, we have one number here to the right. We have two numbers here, so we know our answer needs to only have one number. If we do that problem or that subtraction, we get 14.67, but we know that that has too many numbers in it, so we would change this to 14.7. And then lastly, don't forget PEMDAS. Remember your order of operations. So in that, parentheses comes first. So we would do our parentheses first in our math, and then we're going to divide by this. But you can see we're doing multiplication and division. So the rules for significant figures means we go with the least amount of sig figs, which this has two and this has two. So it would be two sig figs. So this would be 9.0. All right. I hope that you were able to understand that and do that well. I'll end the video here, and then you will have one more video for the next section of the chapter of the part that we're going to do.